Hi everyone, in this video we're going to go over the quotient and root test, and in particular this second video is going to go over the root test. So the root test is a test that is very similar to what we have on the quotient test or the ratio test. We're going to have a series for n equals 1 to infinity of an, a series with non-zero terms or positive if you will, and we're going to define L as the limit when n goes to infinity of the n root of the absolute value of an. Notice that we're going to assume that the limit exists, because if it doesn't, then the series is going to be divergent. Now, if similarly as in the ratio test, if the number L is less than 1, then we're going to have that the series is absolutely convergent and hence convergent. If L is bigger than 1, then the series is going to be divergent. And if L is equals 1, the test is going to be inconclusive and the series might be divergent or conditionally convergent. Now, or absolutely convergent too. Now, let's see some examples of this. How do you know when you're supposed to use the root test? Well, the root test comes into play mostly when you have powers. If you have anything power to the n somehow, then that's a good indication that that might be a good candidate for root test. So let's see some examples here. So for the first one, we have the series from n equals 1 to infinity of 3 to the 3n plus 1 over 4 minus 2n power to the 2n. Immediately we know that this is a good candidate for root test because it has a power to the n. So when we apply the root test, limit when n goes to infinity of n root of absolute value of an, notice that this is going to be limit when n goes to infinity of 3n plus 1 over 4 minus 2n. And we're going to think that this can be negative, so we're going to do absolute value. And of course, because this is to the 2n, and then we're going to take n root, then we need to simplify as the next step. Now, just remember that if we have the n root of a number, let's say we have the n root of a, that can also be seen as a to the 1 over n. And that's going to be the key to simplify this, because now then I can write this as absolute value of 3n plus 1 over 4 minus 2n to the 2n, and then because it's 1 over n, then divided by n. And so this is just really a limit when n goes to infinity of this to this square. But now let's divide by n up and down so we can actually simplify the limit. This is going to be limit when n goes to infinity of 3 plus 1 over n, 4 over n minus 2 to the square. And so notice that when this is going to 0, this goes to 0, this goes to 0, and this is just going to go to 3 over minus 2 the square, which is going to end up being 9 over 4. Okay. Now this number is bigger than 1. So by root test, this is divergent. Okay, so this is the case where it diverges. Now let's see another example. Here we have series from n equals 0 to infinity of n 1 minus 3n power 4 to the 2n. So this is a very clear root test example, since we can go ahead and get the root. So now I'm going to go limit when n goes to infinity directly in root of absolute value of n 1 minus 3n power to the 4 to the 2n. So now we're going to write this out. As limit when n goes to infinity of n 1 minus 3n, and then this is 4 to the 2n, and so we might be considering, we might be, if we're not careful, we might end up putting the 1 over n here. We gotta be careful because we actually gotta do it here. Okay. Now, this particular limit is a little bit more harder than usual. This is actually going to infinity up here, because notice that the exponential actually moves faster than the n. So this is going to infinity. And if I consider below, this is going to here, look, let me rearrange it so I can show it. This will be 1 over n minus 3. So this is going to a number like 1/3 to the infinity, which is like kind of like an indeterminate form. Or if we can think about it, this is like going to 0, since we can consider this really as limit when n goes to infinity of 1 over n minus 3. Since this is 1 really, and so this goes to infinity and this goes to 3, so this is like numerically this is like 1 over 3 by a number that is really large, and so this goes to 0. Okay, you can actually take your time to prove that this limit is actually gonna go to 0, but you gotta prove that this one below is gonna go to infinity. So essentially is a numbered power that is growing indefinitely. So this goes to infinity, and then 1 over something that goes to infinity goes to 0. So you gotta be careful there. But in general, this is something that goes to 0, is less than 1, and so that implies by the root test that this actually converges. Now let's go to the next example. We have here something that looks very similar to geometric series. Probably I could just rearrange exponents here. I have minus 5, 1 plus 2 to the n, 1 over 25 n minus 3. So this is there's a lot of clutter in this series. I can probably rearrange it. Let's actually do that. Notice first that I have minus 5 to the 2n, and so I can just simply see this as minus 5, and then minus 5 to the 2n. And this here, this 1 over 25, I can just see it as 5 to the minus 2, and then n minus 3 here. So as you can see, they're the same kind of thing. So now I'm going to rearrange a little bit more this. This is n equals 4 to infinity, and then it's minus 5, and then minus 5 to the 2n, and then this minus 5 this 5 here. This become 5 to the minus 2n plus 6. So maybe I can rearrange this so it's not a minus 5 anymore. So notice that minus 5 can be seen as minus 1 to the 2n times 5 to the 2n. This is just a split in this term here. And minus 1 to the 2n, this is just going to be 1 because this is minus 1 to a positive power. So now we're just rearranging this, and everything is going to be simply this is 1, this is minus 1. I can get a minus from here, so I'm going to get a minus out. So minus 1. And I'm going to have 5 to the 2n plus 1 from this term and this term. And I'm going to have 5 to the minus 2n plus 6. And so this is going to be a fun case. Because just by rearranging, then I'm going to have that this is 5 to the 7. And so obviously this is the integral of a constant. And then because it's the integral of a constant, this is going to just be infinity, and it's going to be divergent. So sometimes things that might look like they are something for the root test, they're not even going to be for the root test, because you can just simply get rid of some of the terms that are being used. Now, of course, I can still use a root term in here, and I should get the same result. Consider this sequence here. I'm going to do limit when n goes to infinity of as n root of this minus 5, 1 plus 2n, and 1 over 25 n to the minus 3. This minus 5 to the 1 plus 2n because this is just a minus 1 to a positive to a regular odd value here. Then we can consider this always minus 1, and it's going to be eaten by the absolute value. So the real n, I can just think of this as just 5 to the 2n plus 1, and then I can do something very similar to what I did before in here. And this is going to be 5 to the minus 2n plus 6 at the end, and this is still going to be the end root of this. And then at the end, this is just again 5 to the 7 over n, right? And so notice that if I'm using now n going to infinity, then this is just going to be 5 to the 0, which is going to be 1. So because we got a 1 here, then our test is going to be inconclusive. So root test is inconclusive. So our best bet is still what we did before here of rearranging all the terms of the series to get a conclusion. All right. So now let's go to another example. We have this n over 2 to the n. And this looks like it's going to be divergent right away. Because if I take limit when n goes to infinity of n root of a n, this is just limit when n goes to infinity of n over 2. That's it. And this goes to infinity. So just by this being bigger than 1. Root test tells me that it's divergent. One last example will be this one here. We have the series from n equals 1 to infinity of 1 over e plus 1 over n power to the n. Now this looks like kind of similar to an exponential. So I tend to think that this might be divergent, but I don't know yet. So let's take a look. You don't want to be guessing because sometimes your guesses are going to be wrong. So this is limit when n goes to infinity of the n root of absolute value of 1 over n. So if we take the root, it's going to be actually 1 over e plus 1 over n. Oh, so notice that this goes to 0, and so this whole limit goes to 1 over e. And this is less than 1. So this actually is going to be convergent by root test. Okay, so you gotta be very careful when you're doing root tests and ratio tests. You cannot just guess with your initial impressions of something, and you actually gotta go through the limit and see if your series is gonna be convergent or divergent by the particular test that you're using. Anyway, that's the end of the examples for the root test.